Welcome back to The Explainer. Today, we are diving deep into one of the most fundamental data structures in all of computer science, the linked list.
All right, here's the game plan. We're going to start with the why. The problem that arrays can't quite solve. Then, we'll dissect a linked list, piece by piece. We'll see how it actually works, peek at some code, and then wrap up by showing you where these things are hiding in plain sight.
So to really get why linked lists are such a big deal, you first have to understand their main rival, another super common data structure, the array.
This slide really nails the fundamental trade-off. Think of an array like a bookshelf. Everything is in a specific, numbered slot. You want the fifth book? You just go directly to slot number 5. It's super fast. But a linked list, that's more like a scavenger hunt. You start at the beginning, and each item gives you a clue that points to the next one. To find the fifth item, you have to follow the first 4 clues to get there.
So if arrays are these rigid bookshelves, how in the world do we build this flexible chain? What are the links actually made of?
Well, it all starts with this one tiny, clever building block. We call it a link, or sometimes a node. And you can just think of it as a little box with 2 separate compartments inside.
Okay, so in the first compartment, you put your stuff, a number, a person's name, whatever data you want to store. But the second compartment, that's where the magic happens. It doesn't hold data. Instead, it holds the memory address, the location of the next link in the chain. It's literally a pointer, a signpost telling you exactly where to go next.
And this is how we string them all together. All we need to know is one thing: where does the list begin? We call that our first reference. From there, it's a journey. You follow the pointer from the first link to the second, from the second to the third, and you just keep hopping along until you find a link whose pointer leads nowhere. We call that null. That's the end of the line.
All right, so we understand the structure now. We've built the chain. So let's play with it. Let's look at the 3 most fundamental things you can do with a linked list.
Let's say we have our list, and we need to find a specific item. We already know we can't just jump straight to it like we would with an array. So what's the plan? You got it. It really is like that scavenger hunt we talked about. You have to start at the beginning, at that first link, and you follow the clues, the next pointers, from one link to the next. At every stop, you open the box and check, is this what I'm looking for? And you just keep going until you either find your treasure or you hit that null dead end.
Now this is where linked lists really start to shine, how incredibly easy it is to add new items, especially right at the front. So how would we go about sticking a brand new link at the very head of our chain?
It's this beautiful, simple 3-step dance. First, you create your new link. Then, you tell it, hey, your next stop is whatever used to be the beginning of the list. And for the grand finale, you announce to the whole program, everyone, this new link is now the official start of the list. And that's it. We've just added it to the front without having to move or shift anything else. It's so efficient.
Deleting from the beginning is just as elegant. Seriously, it's just the reverse of what we just did. How do you think it works?
It's almost too easy. We just change our main first signpost to point to the second link in the chain. And by doing that, the original first link is now orphaned. Nothing points to it anymore. It's just floating out in memory, and eventually the system will come along and clean it up. The list now just starts one step further down the chain. Simple as that.
Okay, so that's all the theory. It sounds good on paper, right? Let's take a quick look at some Java to see how these ideas actually turn into real working code.
First up, we have to define our link class. And check it out, it has the exact 2 compartments we were talking about. One variable, in this case an integer called idata, to hold our information, and another variable, a reference of type link called next. That's our pointer. That's the clue to the next link in the chain.
Then you have the linked list class itself, which is kind of like the manager of the whole operation. And what's wild is that it only needs to keep track of one single thing, that first link. That's the gateway to the entire list. All the logic for adding, deleting, and finding things, that all lives inside this one class.
And remember that 3-step dance for inserting a new item? Take a look at this code. It's a perfect line-for-line translation of the concept. Line 1, create the new link. Line 2, point its next reference to the old first. Line 3, update first to point to your new link. It's a direct one-to-one mapping of the idea into code.
So why does any of this matter? Where does this stuff actually get used? You might be shocked to find out you've been using linked lists constantly, probably for years.
Seriously, you've been using these without even knowing it. Every time you hit next to go to the next song in your playlist, or previous to see the last photo in a gallery, you are walking along a linked list. The back button in your web browser? Yep, that's often just following a pointer to the previous link in your history chain.
They are the invisible backbone for so many of the simple, sequential things we do with our computers every single day.
And that's why this quote is so on the money. They are a true cornerstone of programming. Right after arrays, they are one of the most essential tools in any programmer's toolbox. Their incredible flexibility makes them the perfect solution for a huge range of problems.
Which brings us right back to where we started. We have a problem, we need to store a list of items. How do we choose which one to use?
So, what's the verdict? The truth is, there's no single best data structure. There is only the right tool for the job. It all comes down to one question. Do you need speed or do you need flexibility? If you need instant, random access like a bookshelf and the size won't change much, use an array. But if your list needs to be alive, to grow and shrink and change constantly, you need the elegant flexibility of a linked list. And knowing when to use which, well, that's what makes for smart, efficient programming.